Okay. Actually, where did we stop for the test one? Can somebody remember? Hello.
Yes, sir.
Can someone remember? Okay, what was the last topic we covered in test one? I think it
Mass
was.
capacitance, sir.
Okay.
So junction capacitor.
Did we include that? Okay. Band bending, all those stuff. I don't think
Sir,
so.
lambda base.
Lambda based rule.
Lambda based rules. Okay.
No, sir.
I think lambda based rule was included in that test.
Yes, sir.
If I'm not wrong.
Yes, sir.
So after that, if we can remember what we have done, so let me just go back to this and then try to find out. Have we included the process, CMOS process? Have we included? Sorry, fabrication process.
No, sir. No, sir.
I think from there we have to start.
Yes, sir. Sir, last one is the capacitor.
Capacitance is over, sir.
Yes, sir.
Okay, the mass capacitance, CGS, okay, all those things. Okay, from there,
Yes, sir.
let me just look at my earlier notes. Okay, where I'm having, I don't know where it is. Okay, this is, I think we have converted solution. Oh, this is that test one. Okay, we have covered till here. I think fabrication process, from there we can give it for test 2 now. Am I correct? Hello.
Sir, voltage transfer characteristics.
Of inverter, VTC.
Yes, VTC.
VTC of inverter. And then we had the process steps for, okay, it can be either CMOS, it is. Did we discuss okay, twin tub process? Twin tub. Hello. Did we discuss this? Okay, N-well was discussed, no? Hello.
Yes, sir.
Okay, how about P-well? Can you just think of doing a P-well CMOS process and then think of realizing CMOS gates? Hello. Assume that if I ask you to realize some logic using P-well process, are you then in a position to do it? I just want the answers. Hello. Hello. Can somebody unmute and then say what is the answer? Suppose if I ask you to do a CMOS inverter fabrication process step using N-well process. Are you then in a position to do it? Hello.
Yes, sir.
Yes, sir.
P-well is not done, sir.
Need not be done. So you should be in a position to change your gears and then say, okay, what is actually in N-well? What happens in N-well process? What happens? You start with which substrate?
P substrate.
You start with P substrate. So you can have what is that? P plus.
diffusion.
You can have P plus diffusion. Sorry. What
P
you can
plus
have? P plus diffusion. You can realize a PMOS transistor or NMOS transistor. What can you realize on P substrate? On P substrate, what you can
Sir,
realize?
N well diffusion.
No.
N plus diffusion we have to.
No. What I'm asking you is, on P substrate, what is that you can able to grow? Is it N well or P well? Sorry, is it NMOS transistor or PMOS transistor?
NMOS.
What is the substrate for realizing NMOS transistor? Here,
P substrates.
P substrate. So on P substrate, shall I put N plus so that you can have NMOS transistor?
Yes, sir.
How do you realize on the same P substrate a PMOS transistor?
Sir, by placing N
By
well.
having N well. By having N well, you have P plus,
Fusion.
you can just have PMOS transistor. So you have a combination of NMOS and PMOS, which is CMOS using N well. Am I correct?
Yes, sir.
Can you think of doing CMOS using P well? So if
By
it is,
taking
you
N
start
substrate.
with N substrate, you realize PMOS transistor on this parent substrate, you'll get PMOS. If you want to have NMOS, you need to have P well. Then you have your N plus, which is your what? NMOS transistor. Are you now having NMOS as well as PMOS on a P well? That is the only thing. So it is not again a whole lot of thing we are supposed to redo it. Instead of starting with a P substrate and having a N well, you start with the N substrate and have a P well to realize PMOS transistor and NMOS transistor. Correct? What is this twin tub corresponds to? In this twin tub, you can see something like this. Can you tell me what is the difference between okay, this is one such circuit. Okay, we know that okay, this is NMOS transistor. This is drain, source, drain, source. There's a drain, source. There's a drain, source. Correct? Do you know that okay, this is bulk terminal? Correct?
Yes, sir.
Okay, this is source. What is the difference between these two circuits? These two type of stacking of NMOS transistors here and here. What is the difference? Hello. No difference, or is there some difference?
Sir,
Difference is there.
sir, in left side, bulk potential at bulk and source are same.
Here.
Yes, sir.
Okay, here.
Here, both are at different potential. Bulk is at zero
Only for the
potential.
first one. Only for the first one. Of course we call it as VSB, body bias. So we call it as body bias. So body is biased to ground in all these cases. In all these cases here, body is there at a, of course body and source are at same potential. That's why this is voltage between source and bulk is equal to 0. Here VSB is not equal to 0 except the last one. Can you see the last one? Source and bulk are same potential in the last one, whereas the subsequent they are not VSB is not 0. Correct? So that's why what is the impact of this VSB on the entire process is, so of course VTH is equal to VTO if VSB is equal to 0, because we have threshold voltage O, that is VTH is equal to VTO if VSB is equal to 0. VTH is equal to VTO plus some portion of VSB. Can you see now? this threshold voltage not only depends on VTO, but it also depends on what is source to bulk potential, some portion of it. So if you want to have all the transistor to have same VTH, then source to bulk voltage have to be 0. You have to have something like this. You have to have this bulk and source should be at the same potential. They should be at the same potential. Assume that you have around different circuits here. So this type of circuit is not possible to realize here because you have a single bulk. Because if you ground this bulk, so all the because can I realize n number of transistors on a single bulk? So can I have this as my n? Assume that this is my p substrate. This is n plus. So I'll have one more n plus here. Assume that there is a p plus which is the bulk. There is a p plus which is the bulk. Assume that you have some circuit which is realized. Can you see now? This p plus which is connected to p is actually something like this type of connection. All the bulks are connected to same point. Hello. When all the bulks are connected to same point, and if the source, assume that this is the source which is connected to of course assume that this is source which is grounded here. If this is the source which is connected to drain of this, and if this is the source which is of course this is the drain which is connected to the next source. Can you see here the bulk and the source are at different potential? Sorry. See now, this is your bulk now. This is your bulk. This is source. This is drain. This is source. This is drain. Of course, fine. This is again assume that this is source. Can you see now? I want to stack like this. I want to stack the transistors like this. So this is my source. So I just connected this. I'm just putting it this way. I'm actually putting it this way. Can you see this is source, this is source, this is source. This is the bulk which is connected to ground. Can you see this bulk is connected to ground, this bulk is connected to ground, and the bulk of the next transistor is connected to the substrate. So it is something like this type of connection. So if you are stacking the transistor something like this, so this will not give VSB equal to 0 for all the transistors. Meaning I will end up with something like this type of situation. I'll end up with something like this type of situation. If you want to have something like this, I will go with twin tub process. So twin tub process is one to realize each and every NMOS transistor. You have, of course, you have a substrate that is NRP. You have a N well. You have a N well. You have a P well. So N well is used for realizing PMOS transistor, and then P well is used to realize NMOS transistor. Likewise, you're going to have two tubs to realize their counterparts. If you are having a N well, I will realize a PMOS transistor. If you have a P well, I will realize a NMOS transistor. Nothing will be realized on the substrate. So you have each and every tubs which are used to realize PMOS transistor or NMOS transistor depending on the well. So in such case, you can have exclusively the bulk and source can be shorted here. Bulk and source can be shorted here because they are there to exclusive to that particular well. So if at all if you want to have something like this type of circuitry, you will go for twin tub process. So this tub is nothing but like well. So you have two wells, one for N well, other is for P well. So this is again twin tub process is used to realize the CMOS logic. Correct? Of course, the process is instead of having the diffusion done over here, you'll have a one more P well process. P as well as N will make a twin tub process. So that will be the process steps that are involved in realizing any CMOS case. What is the next topic we discussed? ETCF inverter afterwards. Was it MOS capacitors? MOS capacitor using that band bending structure. Am I correct? After this, After that, what we had? We had different, because that will include the CV characteristics and all those stuff. And then we come up with pass transistor. It's VTC, that is VTC of an AND gate, what we discussed. And then we have transmission gates. Then we had what is that? Dynamic logic. And then this is different implementation. So then fifth one, we had arithmetic circuit. So we had adders, multipliers, and of course from today, by the end of this week, you will be getting the material for doing the sequential circuits, so which includes different flip-flops, so D flip-flop, different flip-flops, and of course even the related timing diagrams we're going to discuss. So this is sequential circuits. So this will be the topic for your T2. Is that fine? Okay. If there are no issues in any of the topics what we have discussed so far, so we'll just proceed. And if you have any doubts, okay, let me just discuss maybe in the coming classes. So today we'll start with sequential circuits. So of course, what is the major difference between sequential and combinational circuits? I think all of you can answer that question. Sequential and combinational.
Output depends on pass.
Output depends on the previous state also. So it's not only the present input, it also depends on what is the previous output. So that's your sequential. And of course, for all the sequential circuit, you need to have some clock. So upon the edge of the clocks, some action will take place. That is purely depending on what is the logic you have. So that means to say, do we have some combinational circuit here? Of course, in this sequential circuit, you got million and more. We'll not go to the details of it. And then we have what? We have a memory element. This is your input. You have something over here. Is that fine? This is input and you have an output. So this memory will be popped down to as one of the or a part of your combinational circuit upon the edge of the clock. Correct? Hello. Okay, let us think of realizing SR. So what is this SR latch? Set and reset, Q and Q bar. What is the output? What is the output here? If I write as Qn, Qn, Qn and Qn bar, what is the output for 0, 0? This is not third semester. What is Qn? Qn is the next output. Upon 0, 0, upon giving the clock, what happens?
1 0.
For 0, 0, 1, 0, it will become 1. Will it become 1, 0? Huh?
Sir, it is 0 0. For SRS, it is not defined, sir.
Not
Sir,
defined.
previous state, sir.
Will it be there in the previous state or not defined?
Previous state.
What is that
Previous
actually
state.
SR stands for?
Set and reset.
Set and reset. Suppose if it is 0, 0, what will happen to the output? Will it remain the previous state?
Yes, sir.
How do you represent the previous state?
Q bar.
because Qn
Qn
bar
minus
is there, it is Qn minus 1. Correct?
yes, sir.
It is Qn minus 1 and Qn minus 1 bar. Am I correct?
Yes, sir.
Done. If it is 0 1,
0 1.
what do you mean by R equal to 1?
Resetting of flip flop.
Reset means okay, Q becomes 0. If Q is
0.
0, this is 1. This means you are going to set the flip flop. This is when this is set, its complement is so and so. Correct? How about this? This is undefined, not allowed or forbidden. Correct? We'll
Yes,
say okay,
sir.
why it is not allowed. Why it is not allowed. Of course, all these things happen at the. So whenever you give a clock, correct? So whenever there is a clock is high, then only this is possible. Only when the clock is high, this is your clock. Correct? So you can write it as this is your clock. If it is edge 1, you write it. Suppose if it is simply a level triggered, you simply write it as clock. This is actually level triggered. This is not edge triggered. That's why this is not valid for this particular logic. This is true if you have a clock like this. If you have a clock which is at the positive edge. Now this is not at the edge. This is for the entire level. As long as clock is 1, you're going to get the output. This is S, R. You have a Q output, QR output. Getting the difference? If I write the clock as something like this edge, then this is so and so. Since I'm not having a clock edged flip flop or clock edge latch, it is not having any sharp arrow. So of course this is again SR. You want to have Q. Of course this is Q bar. You can write it that. You can put a bubble or not. Shall we realize this using gates? Okay, let me write the circuit here. Carefully look at this dot. So this is, there is a connection. So this is one output. This is the other output. Okay, we just take this as Q and this as Q bar. Let us assume that Qn minus 1 is equal to 1. Correct? What do you mean by Qn minus is equal to 1? This is 1. Am I correct? Hello?
Yes, sir.
Assume that this is a condition. Clock is 0, S is also 0, R is also 0. If this is 1, out of these transistor, let me just name the transistor as M1, M2. This is now M3, M4, M5, M6, M7, M8. There are different transistors by name M1 to M8. If this is the case, if this is our assumption, which all transistors are on? If Qn, because you need to start with some value, no? If you assume this Qn minus 1, Qn minus 1 is before the clock. If this is 1, so is M1 on? Hello.
Yes, sir.
If M1 is on, what is the voltage at Q bar?
0.
Even though if there was some voltage there, since there is a short circuit from this to this through this M1, so this Q1 Qn minus 1 bar, is it equal to 0? Since this is equal to 0, the same thing is given here. Is M4 on? When M4 is on, what is our assumption of Q is equal to 1? Is it true?
No, sir. 0.
Hey, when Q is equal to 1, is M1 on?
Yes, sir.
If M1 is
0.
on,
Q bar.
is Q bar is equal to 0?
Yes, sir.
When why it is
Sir,
0
Q
means
is
because
1.
it will totally discharge.
Yes, sir.
Then this is 0. If this is 0, is M4 is
Yes,
on?
sir.
Yes, sir.
If M4 is on, is your output is connected to VDD through this?
Yes, sir. 1.
We assume this as 1 no,
Yes, sir.
so it is 1.
Yes,
So
sir.
our assumption holds good.
Sir, Qn minus 1.
N minus 1 is prior to that, prior to applying this. Assume that, okay, now I am there here. Assume that now this is my clock, this is my clock, this is my clock. Assume that if I give the clock, this is actually Qn, this is the time corresponding to n minus 1. This
Okay.
entire time is n minus 1 because n minus 1 is prior to your after application of the clock. So now you are applying the clock, so this becomes Qn. Getting my point?
Yes, sir.
Qn minus 1 is before you apply the clock. If you assume this to be 1, is that assumption holds good or not?
Yes, sir.
Will that holds good?
Yes, sir.
Okay, as long as clock is 0, S is equal to 0, R is equal to 0, will this hold the value? Does the Q remains at 1 and Q bar remains at 0 as long as my clock is 0 and S is 0, R is 0?
Yes, sir.
Because these 4 transistors will be off. Correct?
Yes, sir.
Assume that clock is still 0, and S becomes 1 and R becomes 0. Something will happen?
No, nothing.
Nothing will happen because this is off, no change in the condition. Even though this is on, it doesn't matter to anything. Correct?
Yes, sir.
You can
Yes,
see
sir.
which is the critical input?
Log.
Clock, sir.
Clock. So that's why we are putting the critical input close to the output, because that should minimize the delay in overall okay, clock to Q delay. Fine. So as long as clock is 0, this will never, the Q and Q bars will never change. So that's why in the truth table you have like this. Only when clock is equal to 1, this truth table is valid. Correct? Let me just go to clock 1. Make clock is equal to 1. When assume that, okay, clock is equal to 1 means you are there in this position. So assume that S is equal to 0, R is equal to 0. Does the output remain in the previous value? Even though clock is 1 here, because these two are off, no change the values of Q and Q bars. Will they remain the previous state of 1 and 0? Will they?
Yes, sir.
They will remain the state of 1 and 0. Next, you take again, because now take clock is equal to 1, make S is equal to 1, R is equal to 0. R is equal to 0. What will happen?
Q bar output 0, sir.
This is 1. So this will become, so we assume that
On.
this is 1, this is 0. Am I correct?
Yes, sir.
Our assumption, we are starting with the assumption of Qn minus 1 is equal to 1. This is 1, this is 0. If this is also 1, this is also 1. So whatever charge that was there, will it get discharged? What is the actual charge before I make this 1 here? Was it 0?
1.
A Qn bar, okay, Q bar
Q bar.
n minus 1 was 0, no? This is Q bar.
Yes, sir.
So that was already 0, it remains in 0. because you can see this is clock has become 1, S is equal to 1, R is equal to 0. My Qn minus 1 and Qn minus 1 bar were 1 and 0. Will it remain in 1 and 0 or will it change? Because when this is 1, this is 1, does whatever charge over here, will it discharge through this?
Yes, sir.
Because there was nothing here, because Q bar was actually 0 itself earlier. Correct?
Yes,
This
sir.
is Qn minus 1, this is Qn minus 1, of course Q bar n minus 1. Before this S is equal to 1, R is equal to 0, it was already there in set condition, it remains in set condition. Correct? Because it was already set, no?
Yes, sir.
Since it was already set, it remains in set condition. Assume that, suppose if your Qn minus 1 is 0, if this is 1 initially, before you apply S and R, if this was your initial condition, when you make S is equal to 1, clock is equal to 1, then whatever charge that was here will discharge to 0. Correct?
Yes, sir.
Then it will change the state.
Yes, sir.
Am I correct? Suppose, let us take Qn minus 1 is equal to 0, Qn minus 1 bar is equal to 1, S is equal to 1, R is equal to 0. Correct? With clock coming as a positive logic 1, what is the expected Qn and Q bars? Are they supposed to set or reset? It's actually in reset mode now. This is now reset. So when S becomes 1, will it set?
Yes, sir.
Okay, will it happen here? You can see when this is equal to 1, so do you have 1 here? I have a 1 here. So this is 0 here. So when this is 1, this is 0. As soon as these two transistors turn on, will this charge become, of course, will it start discharging? Correct? Will it discharge? Hello? Will it discharge or not?
Discharge, sir.
Yes, sir. It
If
will
it
discharge.
discharges, now if it discharges to 0, then by that time, of course, anyhow this is 0, this is 0, this is not discharging. So whenever this becomes 0, will this turn on this M4? Because
Yes.
whenever this becomes 0, this will turn on M4. If this M4 is on, does this 0 become 1? Does
Yes,
it 0
sir.
become 1?
Yes, sir.
This 0 will become 1 now. Okay, that condition is verified. Suppose if you make again Qn minus 1 is equal to 1, then Qn minus 1 bar is equal to 0, make R is equal to 1, S is equal to 0, then make clock is equal to something like this. What will happen? What is the earlier condition? What is the earlier condition? What is this Qn minus 1? This is set now. What should happen as per your R and S?
It will reset, sir.
Should it reset? It should reset. Will it happen? See, this is now 1. This will be 1 initially as per this. When R becomes 1, clock is 1, does this 1 discharge to 0?
Yes, sir.
So once this voltage goes to 0, will it turn on this? It will
Yes,
turn
sir.
on this, then it will going to make Q bar as 1, which is your reset condition. When of course this becomes 0, this becomes 1, means it is reset condition. Correct?
Yes, sir.
If both are 1 1, what is the problem? Why it is called as not a load condition if both are becoming 1 1?
So
What
both are discharges, sir.
what might can happen? Suppose if this also discharges, if this also discharges, what would happen? Because
Toggling.
no, if it is 0, both of them are trying to turn on. Correct? This PMOS, both will try to turn on. Then you're going to have both as 1 1, which is not an allowed condition. Why it is not an allowed condition if both are 1 1? Because it's a flip flop. You're always looking at a inverted outputs. If Q is equal to 1, Q bar should be 0, or it's the other way. But if you make them both of them 1 1, the output will try to become 1. Both the outputs will try to become 1, which is not an allowed condition. That's why we say it's not allowed. It's not allowed. If you make this and then if you run it, what will happen is both will become 1. Both will become 1, which is not an allowed condition. Why it's not allowed condition? Because you have its complement as your truth table. Since this is not expected, we never apply both set and reset as equal to 1 and apply the clock. So that's why we say it as not a load. But it will not harm your circuit. You'll still get it as 1 1, but it is not useful for any of your flip-flop operation because you are looking for Q and its complement on the other side. Correct? Okay. Could you notice something over here? Suppose assume that S is equal to 1, R is equal to 0, Q n minus 1 was equal to 0, and then Q n minus 1 bar is equal to 1, and then you apply a clock. What might can happen? we assume that this is 1. Am I correct? Okay, let me just rewrite that and try to find out what is the issue that may can you see this is a back-to-back inverters connected? This output is going here and this is going. Now assume that this is 1, this is 0, you made this 1, this is also 1, this is 0, this is 1. Because this is 1, so will it try to go to 0? Correct?
Yes, sir.
Yes, sir.
Meanwhile, this is also on?
Yes, sir.
Let me name it as this is M2, no? This is M1, M2, M3, M4, so on. Now, is there such condition where you have a bucket, where you want to drain out the water and there is a supply for water from the other end? So you want to see which one is faster. Suppose if this drains out faster, then the voltage level will become 0. Suppose if this is stronger, it will never drop out. Correct?
Yes, sir.
So shall we say this output is a ratioed logic? Now,
Yes.
what I mean to say is the output depends on the dimension of M2. If the M2 dimension is bit low, of course bit narrow in dimension, then will I get a proper transition from high to low? Will it go like this? If W by L of 2 is lesser compared to W by L of 4 and W by L of 3.
Yes, sir.
If the dimension of this is less, what will happen?
Resistance becomes
More, it won't charge that much. By that time it will discharge so that it can flip the combination from this will become 0 and then this will become 1. Suppose if
Yes, sir.
M2 is stronger, what will happen? Of course, in such case what will happen? I will get a proper voltage of 0 volt because it is allowing it to discharge, and of course even though this is on, this will become off because this is going to discharge fast compared to the charging of this. Meaning you have a opening for this bucket which is wider compared to the tap which is of course opened there. So once it dries out, this will turn off by itself, because this will going to turn off, because whenever this becomes 0, of course what will happen, this will become 1, this is going to turn off this. Correct? Assume that W by L of 2 is greater than W by L of 4 or W by L of 3. What will happen? We
It will not
expected
go
this to
down.
go 0. We expected this to go 0. This may not go to 0 so quickly. It may just be somewhere here, because it is keep pumping the charge and it is keep reducing. It is, of course, you expected the water level to go to fully down, but it is not going, because this is half open, this is also half closed. Okay, water is coming and going. The voltage may not go down to the expected level of 0. So that's why maybe in the textbook you can see this is how the voltage levels. This is W bells. So you can see this will go down here, this will go down here, this will go down here, and of course, if the W bell is not so okay, if your M2 is stronger, then the voltage will not drop down. Can you see here, this voltage is here only, this is not coming down. So this will come down only when the bottom transistor is stronger. Bottom transistor is stronger. So whatever W that is written here is for the bottom transistor. If the bottom transistor is weak, you will not get a expected output voltage of 0. When set becomes 1, it is not becoming 0. This Q bar is not becoming 0, because the set transistor is bit weak here. If the set transistor is strong, then it will come down to 0 quickly. Correct?
Yes, sir.
This is called as this SR flip-flop is a ratioed logic flip-flop. So how do we overcome this ratioed logic problem? Make the dimensions of this stronger compared to M2 for the set side. On the reset side, this and this should be made appropriately comparative. So which should be stronger here, clock and R or the inverter transistor? Hello. Clock and R
Here,
transistor should be stronger compared to the its counterpart in the inverter. Its counterpart in the inverter P transistor, so that this can discharge quickly, so that its charging can be bit slow enough, so that the other can just flip over the combination of your output voltage. Okay.
yes, sir.
So this is one such logic what we thought of doing. Heard of something like this? Okay, hold time, setup time, clock to Q delay, all such stuff in sequential circuits. Heard of?
Yes, sir.
Okay, this is
AMCD.
assume that this is my clock, because for all sequential circuit you're going to have some input and then there is a clock and you're going to get the output. So as we put over here, what are the three important things? Suppose if you take this as your block, can you see there is an input, there is an output, there is a clock. Correct? So upon before I give the clock, how should be your input, and after giving the clock, when do you get the output voltage? So this is your clock. You can see clock is not going in 0 time high, it is taking some time to go to high. This is your input. So let me take an input voltage which is something like variable. Now this indicates that you had some input voltage, there is a possibility of change here. Suppose that if it is 0, 1, 1, 0, something is there, it will change to something like this. Can you see there is a change in the input voltage that is happening here, that is happening here. Can you make out this? Whenever we say this is my data, if this data is written this way, means there is a change happening. So there is a change happening. Where is the change happening? The change is happening if this is your clock halfway, prior to this it is happening. And then let me just take the output here. Output, you had some output, the output will change somewhere here. Fine. this is my output, and of course since we are assuming that this is a edge clock, so after this edge the input may change somewhere here. Of course input is changing here before the clock, input can change after the clock also, what is this here? This is a change in the output because of the input and the clock. We just mark some timings. This is one time, this is the other time, next time is this. Carefully write that. Wrote those timings. From the midway of the clock, before this comes, okay, assume that there is a change in the input voltage. We call this as TS, TH, T, CQ. TS stands for T setup, TH stands for T hold, T CQ stands for T clock to Q delay. Clock to Q means after giving the clock, after what time you will get the output. Q is the output. Can somebody define what is T setup? Looking at that waveform.
Above threshold, it will change. No, sir, that is setup.
There is nothing like threshold. We are not talking
Like,
about voltage, we are talking in terms of timing.
It takes some time to set up.
Okay. Anybody else can try? Can somebody else try? Okay. We know that whenever a clock comes, depending on the input, output will change. What does this will say is, before the clock is valid, if it has to consider the input as a valid input, the input should be stable before this clock comes. So I know that clock is coming at T1. Clock is coming at T1. My input should be stable prior to that time, sometime X. So this is the time. So what I'm saying is, the input should be stable before my clock comes. So at what time input should be stable is called as setup time. The input should be set to that valid value before your clock comes. It is not that whenever your clock comes, whatever your input data, that will not be taken. It will be found in the examples that before your clock comes, the input should be stable before some time itself. Like, okay, if you want to catch a train, will you not go sometime before the train comes? So you cannot just come whenever the train comes, and you cannot just jump in. What I mean to say is, if you are applying the clock at this point itself, you may end up with some erroneous results. So the input, if it has to be considered as a valid input, before the clock comes, the input should be stable before some time. So that before some time is known as setup time, meaning input should be stable minimum, at least minimum by time T setup. If it is not stable at T setup, you may not guarantee that okay, output will not be an expected one. And this T hold, we know that okay, it is not only at this point. Suppose that this is your clock, and suppose if your input is also like this, you can see input is rising here, and then it is dropping over here itself immediately. So it may so happen that if you want to consider an input as a valid input, it should be stable even after the edge of the clock. It should be stable for some time. So that time is called as hold time. Input should be held for minimum time so that you can able to treat it as a valid input after the clock. Before the clock it should be stable, it is called as setup time. After the clock also it should be stable, it is called as hold time. Input should be held in the same state so that it can be considered as a valid input. Input should be stable before the clock comes so that it can be considered as a valid input. That is called as setup time, hold time. So this clock to Q delay is nothing but the time taken by the logic to give the output once your clock comes. You can see this is the clock where it is going high, and this is the point at which you are getting your output available. So clock to Q delay is, it is the time from the rising of your clock, which is the midway here we have taken, to the point where your output makes a transition. So this is clock to Q delay. So what we'll do in the next video or next class is, we will take up an example, try to find out why the input should be stable before some time, why the input should be stable even after the clock, okay, why it should be stable, all those stuff we're going to find out. And we'll also find out how much is the time that it takes to give the output voltage once you give the clock. So with these things, okay, we will be learning more deeper into the understanding of all these sequential circuits. Any questions here? Of course, these times will be in terms of very small time, maybe in terms of microsecond or even nanoseconds. That depends on what is the logic and what family you are working with. Any questions here? So we'll actually quantify exactly know, okay, why it should be stable before and after, and of course what is the clock to Q delay in the coming examples. Okay then.